Hello, ladies and gentlemen, boys and girls. Welcome to the Hartford Astronomy Group. I am Alan Willison, chairman of this organisation, and it's my pleasant duty to welcome you all to tonight's meeting. I see a lot of familiar faces, and I also see some new ones. So if you are new to us, we hope you really enjoy tonight's visit, and perhaps you'll stay around at the end of the talk so that you can introduce yourself and perhaps say a few words to us. We'd be delighted to see you. For the meeting, could you please make sure your microphones are on mute so that the speakers get the screens? And we've got a full program of things to share with you. After my introduction, we've got Martin is going to tell us about what's coming up in the night sky for the next few weeks. Following that, Jerry Stone is going to introduce tonight's speaker, John Davies, who's going to talk to us for about 45 to 60 minutes on missions to near-Earth asteroids. There will be opportunities for you to ask questions, which we ask, could you submit them via the chat facility, and then Jerry will field them at the end. Let me just say Happy New Year to you. One of the later ones, I'm sure, but what a lovely Christmas present we all got this year, didn't we? With the James Webb Telescope actually going. So we wish it well. We know it's well on its way, and we hope everything continues that way. Just a few more weeks and it should be all set up in place. Does a few tests, and hopefully from there on we're going to be startled with lots of infrared images. So without any more from me, can I say over to Martin, and the floor is yours. Martin.
Thank you, Alan. Okay, I'll try sharing my screen. See if I get it right this time. Okay, can everybody see that? Cool. Okay, so start off with the night sky at the moment. When we do get a clear night, which hasn't been too much the last couple of months, but we've had a few clear evenings where we managed to get out and have a look at things. And this evening, what I want to do is just talk about some familiar objects that we will be looking at this time of year. And then I'd like to just show some images of these objects that some of our up-and-coming members of our photography section are taking as well. So if you don't mind me doing that, I'll start off by looking a part of the sky which is due south almost when you get, well, it's dark a lot earlier than it sort of starts off east and then moves into the south. So we're looking at Aldebaran, which is just near the Pleiades and just above Orion. And this particular object I've talked about before, Crab Nebula in Taurus, is a supernova remnant. And if you follow Aldebaran down to Tiangyan and just up a bit, that is where it is. It appears through a small telescope or through binoculars as a little misty blob. But this, I'll just do it. It's a picture that one of our members, Steve Waters, took of it a couple of nights ago. You can see quite a bit of definition and colour in that. So well done, Steve, good image. I'm sure you're very pleased with that. So the next bit of sky we're looking at, which is most people will recognise instantly, is the Orion Nebula, which is in Orion's belt. So if you follow Orion's belt down, the end star is an attack, and there's quite a bit of nebula here. There's a Horsehead Nebula here, and this is the main Orion Nebula, which you can see with the naked eye on a clear night. It appears again as a fuzzy blob. But even just putting the camera an ordinary digital camera on a tripod and taking a picture of that part of the sky, you'll see a bit of colour come out of that. So this next image is by Kevin Noble, which is absolutely superb. This is a wide field image, so we can see the Orion Nebula here and the Running Man, and then here's the Horsehead Nebula here, and then attack. So well done, Kevin. That's a superb image. Just put an image I took, a close-up of the Orion, of the Horsehead Nebula there. Just the telescope that I've got at the moment is quite set up to carry such a small field, so it's just the right bit of equipment for what I was doing at the time. So next piece of sky we're looking at, you can see the ladies there. Most people can see that, the Seven Sisters. And if you come up, you start at thick here, and then work your way up to the next star, and come across slightly, not an object you can see with the naked eye, but it's the California Nebula, which is an area of star growth, and quite a fascinating object. I'll just show you, if you just click on that. This image here taken by Steve absolutely gives you a better idea of what you're seeing here. So you can see the amount of stars are in this area here, but you can see this is just a huge nebula. It's meant to look a little bit like the map of California, hence its name, the California Nebula. But that again is a spectacular image. Also showed you the Pleiades a minute ago. So this is taken by Dan Miller. Again, you can see the nebulosity. He's got really nice sharp stars here. Beautiful picture. Well done, Dan. So I'm really impressed with the way that our members of our photography section are really coming in. This one wasn't taken by any of our members, but by Damien Peach. But I did speak about Comet Leonard last month. And this he took on the 2nd of January, but it's such a spectacular picture. I thought I'd show everybody. You can see the streams of material coming away from the comet being thrown back by the solar wind. But that's a pretty spectacular image. Oh, that's not come out very well. So the next one I talk about is a discovery that's been made, a supermassive black hole. They think this is the biggest one they've ever discovered, Ton 618. Already has a size of 100 of our solar systems. It's been devouring matter for billions of years, and it's the largest cosmic object in the known universe. Just reading a little bit of the information here. The black holes are cosmic objects possessing intense gravity that traps matter that gets close to it. They're normally born from huge stars that when they end their lives, they explode in a supernova, and then the matter that's left in the middle is compressed down by the gravity into a high gravitational area. But they feed on other black holes and other stars. Anything that comes within their gravitational influence is drawn in. So it's one of the largest black holes that have ever been discovered. I thought it was quite an interest. There's an image there of what they think a black hole would look like. You can't actually see a black hole because the light can't escape from it. So what you can normally see is the disk of material that's going into the black hole inside. So just to give you an idea of the size of this thing, the inner ring there is meant to represent our solar system, but not just as far as Neptune, but right out to the minor planets and ice planets that are on, right out near to the Oort cloud, and this is the diameter of the black hole. So it is supermassive. So there's a little bit more information there about it, about the area of circumference of 53 million UAs, which is a astronomical unit, which is the distance from the Earth to the Sun. So we talk about a very large area. Thought this was quite an interesting one. Japan are building a wooden satellite to put in space. So that's actually recyclable, isn't it? So the device will be shaped like a cube, 10 centimetres side. We will include equipment requiring for functioning. So it's due to go up this year on December, the end of the year, 31st. I thought that was quite an interesting thing. A wooden satellite, you would have thought would be possible. So here's a little bit more information. Here's a picture of what it will look like. I think it's made of, I can't read part of my section there. It's just made of normal wood, really, with the electronic components inside. Following the conclusion of the mission, experts plan to determine whether wood is an experimentally benign material for space construction. This other bit of information is about a gigantic arc that's been discovered, 3.3 billion light years present. Galaxies spanning 3.3 billion light years is amongst the largest known structures in the universe, and been challenging astronomers' most basic assumptions about the cosmos. So that may be something to hear a little bit more about going forward. So this is an image of how the arc, I think it's a section here running through here, shows a grey region shows areas of absorbed magnesium, which reveals the distribution of galaxies and galaxy clusters. Talk about blue dots, but I haven't got a bright image here, so I can't enlighten on what the blue dots are. I assume these are the blue dots. It was discovered by Alexia Lopez, University of Central Lancaster in the UK. So that's quite interesting. Lopez was assembling maps of objects in the night sky using the light from 120,000 quasars, distant bright balls of galaxies with supermassive black holes, consuming material and spewing out energy. I like this image here. I found this on Facebook the other day. This is looking at our galaxy. I think it was taken in Australia. But it's I'll just read what's over here. On a clear night, the Milky Way dominates the sky above Australian outback, arching overhead in a way never seen in the northern hemisphere. We only see sections of it in our hemisphere. As well as it looks up to our eyes, only a tiny part of the spectrum of light emitted from the galactic plane, so we can only see the visible light. So astronomers have pieced together an image to show how the region would look if our eyes could see the frequencies of FM radio. So that's a radio image. So quite a spectacular image. Last piece of information here. Around 10 million years ago, several unannounced blasts swept up gas around a one-time star, clearing a cavity 250 light years wide. All the interstellar gas was pushed to the edges, triggering a new generation of star formation. So that was quite interesting that they can actually see that in another galaxy. So I thought that was quite interesting. So really makes you wonder, once James Webb is in place and imaging, what sort of stuff we're going to be able to see in the future. And that really ends all the information I've got. So thank you very much for listening. I'll pass you back to Alan. I can stop sharing.
Okay, well, thank you very much indeed there, Martin. A lovely explanation of things that we can be looking out for. I have one question, if you know the answer. Which part of the sky is Comet Leonard actually in, if we wanted to go and find it? Do you know where that is?
I think it's. I don't at the moment. I mean, I could look at my last week because it was dropping below the horizon, so it's in a different part of the sky. I just picked that image out because it was on Damon's site. I don't think it's so visible now because it's now going away from the sun. But why John's talking? I'll have a quick look, see if I can work out where it is for you.
Okay, thank you very much indeed, Martin. Does anybody else have any questions that they'd like to ask Martin while he's here? You can either type it in or unmute yourself and quickly say something. Well, it certainly sounds like everyone feels satisfied about that. So once again, thank you, Martin. I'm now going to pass you over to Jerry, who's going to introduce tonight's speaker. So over to you, Jerry.
Thanks very much, Alan. And yeah, welcome everyone to our first meeting for 2022. And as Alan has already said, we've already had the great news of actually seeing the James Webb Space Telescope finally launched after all these years. And now it has completed its deployment. All 178 pins did what they were supposed to do, and now we just have to wait for it to get to L2 and establish itself in position. It's quite something. That's going to be around July that's planned, which will then mean that there's only 3 years to go until the 50th anniversary of the first time that John and I met. And that was in America when we went to see a different launch, the Apollo-Soyuz test project. We saw the American half of this. This was the first international manned space flight. Russia launched a Soyuz from Baikonur, and then a few hours later, the very last Apollo was launched from Kennedy Space Center, and we saw that go off. John, since then, has done some interesting work, to say the least. I mean, he's worked at the Royal Observatory at Edinburgh. He's also done some work in Hawaii, so for which we can all be fairly jealous. And his particular interest of his has been that of near-Earth objects. Now, I'm sure that many of you will have seen Meteor or Deep Impact or Armageddon, which I think John would agree don't necessarily present the best possible ways of avoiding the Earth being hit by bits of rock from outer space. And there's a heck of a lot more of those bits than most people realize. In fact, there's more chance, I think, of being killed by a meteor than there is of winning the national lottery. So next time you know someone who buys a ticket and you wish them good luck, just you might want to think about that. So John's going to look at 2 recent sample return missions to near-Earth asteroids. I mean, the more we know about these things, the better. There's a Japanese spacecraft which has already returned to Earth, Hayabusa 2, and the American OSIRIS-REx mission, which has completed its contact with an asteroid called Bennu, and is on its way back to Earth. Not only with samples, but that's one of the spacecraft that has my name on it. So to tell us all about that, I'm going to pass you over to John Davies. John, you just need to unmute yourself. And for everyone else, if you put your questions into the chat, then we'll go through them once John has finished. All yours, John.
Right, thanks, Jerry. If all goes well, you should see my title slide.
Yes, we can.
Right, hello. Yep, thanks everyone. That picture in the background, by the way, was taken at Huntsville on the very trip that Jerry was talking about back in 1975. So yeah, my name is John Davies. I'm an astronomer at the Royal Observatory in Edinburgh. Technically, it's the UK Astronomy Technology Centre, but it's physically located at the Royal Observatory in Edinburgh. And I got involved in asteroid science back in 1983 when I worked on the IRAS satellite, searching the IRAS database for rapidly moving objects. Got me interested in asteroids, and I've dabbled in them ever since. So yeah, as Jerry said, tonight I'd like to talk about 2 sample return missions, and I will wrap up with just a brief summary of the asteroid redirection test DART, which was launched a few weeks ago. So let's get straight to it. Which one of these is it? So let's get everybody on the same page. First of all, what do we mean by a near-Earth asteroid or a near-Earth object? And that is, it's something generally, if we're thinking particularly of rocky objects, we're talking about something which has its aphelion, its furthest distance from the sun, is somewhere in the main asteroid belt, and it sweeps in across the orbit of the inner planets. If it only gets as far as Mars's orbit, it's called an Amor. If it crosses the Earth's orbit, it's called an Apollo. And if it spends more time inside the Earth's orbit than outside the Earth's orbit, it's called an Aten. But these can be just generalized as near-Earth objects. So these are objects which cross the orbit of the Earth. Now we know that objects in such an orbit cannot survive for very long. They will either have a gravitational interaction with the Earth or the sun, which will fling them out of the inner solar system completely, or they will collide with the sun, or they will very occasionally collide with the Earth. The average lifetime of a near-Earth object is about 10 million years. And the fact that the solar system is much, much older than that is telling us that either there were a humongously large number of these things originally, far too many than there could have been in practice, or they are constantly being refreshed. And that turns out to be the right answer. The near-Earth object population, neglecting the odd comet that gets trapped, but the asteroid population is being refreshed from the main asteroid belt. But that's not a simple thing to do, because you can't boot an asteroid from the main belt to an Earth-crossing orbit in one go. The energy required to push it or to kick it into an Earth-crossing orbit is so large it would disintegrate the asteroid. So there has to be a more subtle way of doing this. And this is done by gravity. If we look at the distribution of asteroids in space, so vertical column is the number of asteroids, the bottom line is the distance from the sun, the typical distance from the sun, we see that it's not a smooth curve with a bump in the middle, but there are distinct gaps in it. Those gaps are orbital periods where the orbital period of the asteroid is an exact multiple of the orbital period of Jupiter. If an object is in such an orbit, then Jupiter's gravity will give a little pull, but it will give it a little pull every time it goes around. And over time, those pulls will nudge the orbit and flip it suddenly into an Earth-crossing orbit. And these things are called Kirkwood gaps, after the astronomer first realized that they existed. So now we don't have to generate enough energy to throw something from the asteroid belt directly to the Earth. We merely have to nudge it from its stable orbit into a Kirkwood gap, and then let Jupiter's gravity do the rest and throw it towards the Earth. So that's how we make these. That's how these things are made. You only need a relatively small collision in the belt to push something into a Kirkwood gap, and then gravity will do the rest. And the other conceptual thing I just want to introduce at this point before we get to specifics is the context of asteroid families, and you'll see why in a few minutes. So if we plot the orbital information about the asteroid in a slightly different way, this time I've got the angle between the Earth's orbit and the orbit of the asteroid, its inclination on the up scale, and the typical distance from the sun along the bottom. What you see is not, again, not a smooth curve, but you see random, what appear to be random clumps. There are a lot of asteroids with similar orbital elements, and there are some orbital bits of orbital element space which are not occupied at all. And what we think happened here is, let's take the Hungaria family up in the top left-hand corner. What we think is a much larger asteroid once existed in this orbit. It was impacted and destroyed and chipped into a large number of pieces. And those pieces are still basically in the same orbit as the original parent object. So we call this the Hungaria family because that Hungaria is the largest object which survives. And all the other, but Hungaria and all the other bits in similar orbits were probably once part of a much larger asteroid. And there are many of these families. These are just some of the better known ones. So when I say an asteroid family, what I mean is a bunch of asteroids with similar orbits, which were probably once all part of the same larger object, which somehow got smashed up. And it's in that smashing up, of course, that things can be flicked into a Kirkwood gap and hence into an Earth crossing orbit. So now we've got that those definitions out of the way. Let's look at the first of these missions, the Japanese Hayabusa 2. The clue's in the name. Hayabusa 2 is a follow-up to the original Hayabusa mission, which went to asteroid Itokawa about 20 years ago. It was a small spacecraft. It successfully rendezvoused with the asteroid. It also made an attempt to grab a sample. That attempt was marginally successful. Collected only a few grains. Most of the other things that it was supposed to do didn't work. So the Japanese decided to try again with an improved version of the mission, Hayabusa 2. The target selected for Hayabusa 2 was this asteroid, number 162173, Ryugu. You don't have to read all this stuff, it's just there for the record. It's a C-type asteroid, so it's carbon-rich, relatively unevolved. So asteroids can be classified into different types depending on the spectra. You have metallics, which were probably the core of exploded asteroids, and you have the carbonaceous asteroids, which haven't been processed very much. It's a potentially hazardous asteroid. It's a member of the Apollo class, so it crosses the Earth's orbit, and it's in an orbit which, although it's not likely to collide with the Earth at the moment, it might collide with the Earth at some time in the future. So these are called potentially hazardous asteroids. It's about 900 meters, 3/4 of a mile in diameter, and it rotates on its own axis in 7.5 hours. So it's not very big, but it rotates 3 times a day. To get there, Japan launched their spacecraft on one of their indigenous rockets. It's an H2 rocket, it's called. And as we'll see for the other missions I'm going to talk about, the first thing you do is you go around the Earth a couple of times. You come back to the Earth, and then you gain a gravitational swing by of the Earth, which throws you out into an orbit to intersect the asteroid. That's where you don't need a lot of rocket power in your satellite itself. So this is the track that Hayabusa followed. It was launched in 2004. It swung past the Earth a year later, and that tipped it into an orbit which sent it out to rendezvous with the asteroid in July 2018, almost 3 years ago now. And when it gets there, the first thing it does is you don't so much go in orbit around these things, just rendezvous with them, because their gravitational field is, of course, very weak because they're very small. So Hayabusa put itself in what it called its home position, a distant, by which they mean 20 kilometers, orbit from the center of the asteroid. Remember, the asteroid is only 0.5 kilometer wide, so it's only 20 times the distance from the diameter of the object to the orbital position. Hayabusa sits in that position for a while, maps the asteroid carefully, studies it, and every now and then it would close in on the asteroid, both for better resolution imaging, higher resolution imaging, and also to gain experience for the controllers on how to do this, because their plan is to land on the asteroid and sample return. So they need to be able to navigate accurately in the presence of this weak but not very smooth gravitational field. So it turns out to be a more or less diamond-shaped object. It's got an equatorial bulge running left to right across the left-hand picture. The albedo, the reflectivity, is very small. It's only about 5%. That's darker than coal. This is a really black object. I mean, these things, the pictures, they look quite gray and reflective, but in practice, They're very, very dark. And from the images, you can get the volume, and from the spacecraft dynamics, you can measure the gravity field and get the mass. And it turns out that the density of this thing is very low. It's only about 1.2. That's not much denser than water. So what that's saying is that it's clearly made of rock, but it can't be solid rock. It must have lots and lots of voids. There must be 50% of its volume must be empty space, and 50% boulders. So it's a rubble pile. It's not a solid object. It's just a collection of boulders. It has many impact craters, which means since you wouldn't expect the asteroid to receive many other asteroid impacts if it was in an Earth-crossing orbit, it means it probably formed in the main belt. There also seems to be a lot of small stones on it, so it's quite possibly when it was formed or when it was ejected to the into the Earth-crossing orbit, it might have shed some material, so there might be meteorites connected with this particular object. And that equatorial ridge along the middle is caused because the asteroid is spinning so quickly. I did have a much more complicated slide of this, but I took it out because, frankly, the talk was getting longer and longer. But if anybody wants to get into the nitty-gritty, we can bring the slide up later on in the discussion. So the first result we see is that this object has got a lot of boulders on it. It's in fact covered in boulders, and that's quite a problem because, as with the other target, Bennu, the assumption was it would have fairly large smooth areas on which you could sample, but it turns out not to be the case. So Hayabusa carried a number of lander experiments. The first of these were the so-called Minerva landers. They were deployed on the 21st of September, and a few weeks later, they deployed another lander called Mascot. So we'll look at both of those in turn. This is the Minerva experiment. It's called Minerva 2 because there was a Minerva experiment on Hayabusa 1. Unfortunately, they missed the asteroid completely when they were deployed, so they didn't land. So this is Minerva 2. There are two parts of the Minerva experiment. This is part 1. And part 1 contains two spacecraft, 1A and 1B. There is a Minerva 2-2, but that failed before deployment, so it was never actually launched. To give you a scale, these little landers are 18 centimeters in diameter and 7 centimeters tall, and they weigh about 1 kilogram. So they're the size of a sponge cake. I mean, they're not very big. They have solar panels, and they're not so much rovers as hoppers, because they have inside a vibrator mechanism, not unlike the thing you might have in your mobile phone, which, because the asteroid's gravity is so weak, if you twiddle the vibrator, it's enough to make the thing jump up in the air and move across the surface. So these things are not really rovers, they're more hoppers. But the idea was they would be dropped, they would simply float down to the surface. You don't need retro rockets because there's next to no gravity. Once they land, they can use these vibrator mechanisms to hop around to different locations. And here are some pictures from these Minerva landers. The A lander returned 609 photographs over a period of 36 Earth days. That's 113 rotations of the asteroid. The B lander was less successful. It survived only 3 Earth days, 10 asteroid rotations, and returned about 39 images. These are some of the earliest ones that are released. They are not, they lack one crucial piece of information, and that is they have no scale bars. And I have tried and tried to get scale bar information, because without knowing how big these pictures are, it's very difficult to understand what you're actually seeing. I'm guessing that most of these objects, these little stones, are just that, things a few centimeters across rather than meters. So they're stones and pebbles rather than boulders, but without a scale bar, it's difficult to tell. And they are very wide angle images. You can see the distortions towards the edge. But nonetheless, they were the first pictures returned, I think they're the first pictures returned from the surface of any asteroid. I was told by somebody else who knows these things that the part of the reason why they're so poorly calibrated is that these are almost student experiments. I mean, they were sort of done on a shoestring, but I am sure eventually we'll get some proper scientific analysis of these images, but until we've got some scale information, it's really quite hard to make much sense of them. The second lander is this thing, the Mobile Asteroids Surface Scout, or something, some constructed name like that, mascot. This is a bit bigger. It's 30 by 30 by 20 centimeters. So it's about the size of the business end of a microwave oven. You could just about get this in my microwave. It weighs 10 kilograms, and it was provided to the Japanese Space Agency by the French and the German space agencies. This was released from the mothership at an altitude of, from an altitude of 51 meters. And it took, I think, I've got it written down, let me turn it over, 6 minutes. It took 6 minutes to fall the 51 meters to the surface. It bounced around the surface for several minutes before it settled, and it landed upside down. Here are some pictures of it. The blue square is magnified. The blue square on the left is magnified on the right. And what you can see is the shadow of the Hayabusa spacecraft in the bottom right-hand corner of the picture, the body of the thing with its 2 solar panels, which are 4.5 meters wide. You can see the mascot spacecraft itself falling towards the surface, and the shadow thrown by mascot onto the surface as it falls. You know, for those of us who grew up with the old Apollo era images of grainy, black and white, smudgy photographs, if you were lucky, this is just fantastic stuff. The mascot landed successfully. It landed upside down, but it had a little spring-loaded bar that flipped it the right way up. Unlike the Minerva landers, it had no solar panels. It was just running off batteries, and it had a lifetime of about 17 hours. Here is a picture from the surface. This one has got scale bar on it. You can see there's a 5 centimeter bar in black and white in the center. So we're looking at quite fine detail, in fact, very fine detail here. And the thermal data, the data from the instrument on the lander, which measures the amount of heat being radiated from the asteroid, tells us that the material has very high porosity, i.e. it's not a very good conductor. Solid rock is quite a good conductor of heat. Powdered rock with lots of voids in it is a good insulator. So it has very high porosity and very low strength. And the images which show that there are many, many small boulders suggest that the surface is unconsolidated. Again, it's not so much a solid surface as a bunch of boulders roughly sticking together. But the really spectacular stuff starts after these 2 landers have been deployed, and that is with the attempts to gather samples. Now, the methodology here was the same as on Hayabusa 1, that the spacecraft lowers itself down to the surface of the asteroid, and sticking out the bottom of the spacecraft is essentially a trumpet. To help it navigate, it pre-drops, and you can see that just the left-hand side, a little target marker to help guide it down to the surface. The object is sufficiently far from the Earth that you cannot fly this thing down in real time with a joystick. The time lag for the radio signals is too long. So this has to be done automatically. So Hayabusa lowers itself to the surface, just touching the surface. And at that point, it releases, it fires a ball bearing down into the surface. And the hope is that this ball bearing will then throw up enough dust, which will bounce its way up the trumpet and finish up in the sample container. And that's what went wrong on Hayabusa 1. The ball bearing didn't fire. So although it touched the surface and lifted off again, it gathered almost no dust because there was nothing to push the dust into the trumpet. However, on Hayabusa 2, the ball bearing does fire and they do get a sample. So here's a picture of the target site just before touchdown. If you want to look at that picture, if you want to look in the bottom left-hand corner, you can see a rock that's split in half. That same rock will be visible in the next slide, slightly up and further to the left. So this is the landing site before the touchdown, and this is the landing site after the touchdown. There's that split rock now on the left-hand side of the picture. And you can clearly see that the touchdown has blown a lot of dust and stuff around because there's a lot of marking surface changes. So the touch and go thing clearly worked on the first attempt. But what you've got here now is a sample of the asteroid surface, which has been exposed to the sun for probably millions of years. Now, I remember when I started in this game back in the 80s, 70s and 80s, there was a lot of debate about a thing called space weathering. There were some people who said that the asteroid surfaces will not be pristine because the sun has been shining on them for millions of years, because cosmic rays have been bombarding them for millions of years. And what you will see is not a raw asteroid surface, but a sort of baked asteroid surface. We now, I think, believe that we now accept space weathering as a done deal, but at the time it was somewhat contentious. So the Japanese decided that they would investigate this, because their first sample grab had grabbed some surface. Now they want something which goes deep below the surface, when they have this audacious mechanism for doing all this. They release a thing called the small compact impactor, which is shown on the left-hand side. And this is what's called this contains what's called a shaped charge. Now, any of you who know anything about World War II, which is probably not many of you, but shaped charges are best known as the warheads of bazooka shells or of RPG missiles, because they're like a teacup shaped explosive. And when they ignite, they direct all the blast in one direction. And if you're sitting in a tank, that blast blasts its way through the side of the hull. In this case, the shaped charge is used to fire a plate, a lump of copper, down towards the asteroid. So the picture on the right shows the compact impactor exploding its shaped charge and flinging a slab of metal down to the surface, which then punches a hole in the crust. So that the explosion doesn't actually occur on the surface. The explosion occurs in the impactor to fling the piece of metal down to punch a hole in the crust. To see if this has worked, the Japanese released a small flying digital camera. That's the thing that looks like a Coke can, just to the top right of the picture. That's just a camera. And while all this is going on, the mothership has retreated behind the asteroid to hide, just in case it gets hit by any flying debris. Here's a picture of the impactor being released from the mothership. Again, sort of thing that people take for granted these days, but to me is little short of magic. But with cheap CCD cameras and lots of bandwidth, you can do this sort of thing fairly easily. And it worked. Here's a picture taken from that little flying camera. It only had a lifetime of a few hours, but it only had to work long enough to photograph the impact. If you look in the top right-hand corner of the bottom picture, you can see the impact actually taking place, and that's magnified in the little inset. You can see material being flung off the asteroid as the impactor smashes into it, digging a crater and thus exposing material that hasn't been exposed to the sun for millions of years. So this is they then had to come back. They waited for the dust to settle, literally. Then they came back with the mothercraft and had a hunt around till they found the impact spot. You can see it very clearly here. Left-hand picture, right-hand corner, you can see this kind of diamond shaped, triangle-shaped rock, looks a bit like Captain Kirk's badge. And just to the left of it, in the second picture, you can clearly see the hole where the impactor has blasted out a fresh crater. So then they send their spacecraft back down again, and this time they're trying to get material that's been excavated from that crater. And again, it works. This was done in July. Here's the spacecraft descending. Now, if you go onto YouTube or search this, you can find a video of this, and it's very spectacular. But my bitter experience with Zoom is that videos don't work very well. So I've just got a still picture here. This is the thing coming down. You can see the sample horn. That's the white thing in the center of the picture, just about to touch the surface. This is a still from the video. And you can see that as the spacecraft touches down and as the probe horn hits the surface, all heck breaks loose, stuff flies off in all directions. And indeed, some of it flies up the trumpet into the sample container. What's all this telling us? Well, I'll just change notes again. There are several methods. There's the remote sensing of the surface from the orbital spacecraft, the spectra and images and so on, and strongly suggests that the surface has got materials on it which have been aqueously altered. That's not to say they have literally been in a bucket of water, but they have been in an environment where there have been active OH ions around. So at some point during its lifetime, the material in Hayabusa has been exposed to water in some form, not necessarily liquid water, but water in some form. And there's been reactions with this water and the chemicals in the rocks to form these aqueous minerals. To do that, you need heat. There are two main ways of doing it. Either you trap during the formation. Now, I should say at this point, we're talking about the parent body of this thing, not Ryugu itself, but the parent body some billions of years ago when the asteroid belt was forming is big enough that it traps aluminum-26. Aluminum-26 is a highly radioactive material. It decays, it generates a lot of heat. That melts the internal structure of the asteroid. That's why the Earth has an iron core, because the Earth also incorporated a lot of aluminum-26. So the aluminum-26 heats up the middle, there's some differentiation, there's some chemistry goes on, and you get this aqueous alteration. It's also possible to heat it up by a series of impacts, but each impact, of course, only heats up the localized area. So if you're going to do a lot of this, you have to have many, many impacts, which integrate and average out to heat up the whole of the interior. So trapped aluminium is the most likely method. So now you have a differentiated asteroid, which has some crust and had some chemistry. It then gets smashed into by something else. And this smashes up the parent body and forms a family. Remember, I said early on that families are collections of asteroids with very similar orbits. So the parent body is smashed up, forms a family, a bunch of objects in roughly the same orbits. Some of them are so close together that they can actually re-impact each other and gradually reform. So they form another much smaller asteroid, which itself is made up of lots of pieces from the first impact. And maybe, again, within this family, there's another impact, which smashes it up yet again. Again, you get clouds of material, lots of boulders, which re-merge to form yet another, yet smaller object, which is the thing we call Ryugu. And that's the preferred explanation of how you can get aqueous material in such a small object, because you can't do it on Ryugu itself. You have to do that somewhere else and then gather that material together. So it looks like Ryugu is not in any sense a truly original asteroid. It's the result of at least one, possibly two major impact events. And that's why it's a rubble pile, because it's a lot of small pieces joined together rather than a single object. And it turns out that there are two asteroid families which have orbital elements sufficiently close that they could be the original parent of Ryugu, and they are the Polona family, asteroid 142. The largest object in that group is Polona. It's 55 kilometers in diameter. Or it could be the Eualia family, asteroid number 495. That's a bit smaller. That's only 37 kilometers. But remember, these are just the biggest fractions, biggest fragments of the original parent body from which Ryugu formed. So what happens next? After staying in orbit a little bit longer, Hayabusa starts returning to Earth. In Hayabusa 1 case, this went very badly. They had lots of technical problems, but they did pull it off in the end. In the case of the replacement mission, it was much more smooth. It departed the asteroid in November, took a year to get back to Earth, releases the sample container in a heat-shielded thing about the size of an ice bucket. It's basically the same sort of thing, like it just looks like a very small Apollo capsule. And it lands in the Australian desert in Woomera in December 2020. So what's that, 2 years ago? A year and a bit ago. And these samples have been successfully returned to Japan, and the sample containers have been opened. This is what the sample containers look like. The one on the left is the original sample, and the one on the right is from the crater after the explosion, after the lander. It looks like a lot of stuff, but I draw your attention to those scale bars. Those photographs are those canisters are only about 10 millimeters in diameter, so there's not actually that much stuff there. In fact, there's 5.7 grams of material. That doesn't sound like very much. For those of you who don't speak metric, that's about one large size licorice allsort or 2 cocktail olives. That weighs about 5 grams. So it's not a huge amount of stuff. On the other hand, it's many, many hundreds of grains, thousands of grains probably. And you can do a lot of science on small grains these days. They have already divided these things up. Here are some of the little sample containers. And again, you can see how much is in each one, about a gram. And for scale, because it's a bit hard to make out exactly how much this is, that's how big these containers are. They're only tiny. They're the size of a penny piece. But we have already learned that the chemistry, I mean, so far the stuff's been examined non-destructively, and it's being divided up, then it's being sent off to labs where they can do things more aggressively, which will destroy the material. But to start with, because it's so precious, you do non-destructive testing, count the grains, do spectroscopy and stuff. About 40% of the material will be put in deep storage for subsequent analysis in the future, as has been done indeed with the moon rocks. Most of the moon rocks returned by Apollo have never been analyzed because they're sitting in a store waiting for clever techniques to come along. But what we find is that the chemistry of these things seems typical of the bulk asteroid. The density is about 1.2, about the same as the asteroid itself, slightly less dense actually, which is perhaps surprising after all the shaking that it's had, but there you go. And it's highly fragmented. So that's a pretty impressive achievement so far, I think, and they're not finished yet. The mothership flew past the Earth when it dropped off the sample container, and the mothership is still working, so there are several mission extensions proposed. One of them is this, to send it to this asteroid number 98943, discovered in 2001, and it would arrive there in July 2026. This object is about 1 kilometer in diameter, sort of stylistically shown on the left-hand side of this picture. It's smaller than a mountain, but it's still 1 kilometer in diameter, so it's about the same size as Ryugu actually. But it can't be. There could be no more sampling. It's the sample mechanisms, it's only got one return capsule, but they can still go there, they can still photograph it, they can still do the chemical analysis from orbit. And then the plan is to go on yet again, returning to Earth using the Earth's gravity to change the orbit again, this time to rendezvous with 1998 KY26, 10 years from now. So if the spacecraft is still healthy, they will hopefully send it to rendezvous with this thing. Now, this is a very small object. It's only 30 meters or so in diameter. And as far as you can tell, for something so small, it's probably more or less round. It spins very quickly, 10 minutes, 11 minutes. And that's telling us that it's probably a single boulder. Excuse me. I said that Ryugu itself, and indeed Itokawa, the Hayabusa 1 target, these are rubble piles. They're aggregates of boulders held together by their mutual gravitational field. And if you spin something like that up, it quickly flies apart. So there are no rapidly rotating rubble piles. The fact that this thing rotates in only 11 minutes means it's probably a single shard. It's probably just a skyscraper-shaped boulder. It'll be very interesting if I'm still alive in 2031 to see what it looks like if they get there. So that's Hayabusa. The OSIRIS-REx, for those of you who are clock watching, this second part is a bit shorter. OSIRIS-REx has this rather contrived acronym. It's an asteroid explorer mission. The security bit is we need to understand asteroids before we can deflect them. It was selected in May of 2011, and its official objective is an asteroid sample return. So in many respects, it's very similar to Hayabusa, except it has no landers. The target for this thing is the little model I was waving around at the beginning. If anyone's got speaker view, you can just about see it. It's called Bennu, asteroid 101955. It's another C-type asteroid. The B is a subset of the C. It's a carbon-rich primitive object which probably hasn't evolved very much. It's another potentially hazardous asteroid with a small possibility of striking the Earth. It's about half the size of Ryugu. It's 500 meters, 600 yards in diameter, and it rotates in 4 hours. OSIRIS-REx was launched by an Atlas rocket, and you see that the trajectory is very similar to Hayabusa. You launch it, it goes around the sun. Once it re-encounters the Earth, uses the Earth's gravity to send it off to rendezvous with the target asteroid. And it arrives there in December 2018. It makes several flybys to get basic shape information, and then it enters orbit around the object. Now, this is 500 meters in diameter. The orbital altitude is 1.75 kilometers. So this is very close in compared to the size of the body. And what we see straight away, as we saw with the Hayabusa target, is that the entire surface is rough and covered with boulders. In fact, some of these boulders are large enough to get distinct names. There's a naming convention for lunar mountains, for seas, for craters, for rills, valleys, but there's no naming convention or there was no naming convention for large stones. So they had to invent one. So these things get the name Saxum, and they can only be named if they're more than a few % of the diameter of the parent body. So some of these boulders are sufficiently large relative to the parent that they're big enough to name. That's just a little aside there. So the entire surface is rough, it's covered in boulders, and the thermal modeling done from the Earth and the radar observations done from the Earth completely fail to predict this ruggedness. They were predicting it would have many fewer boulders, more smooth surfaces, which creates a problem because the sampling mechanism requires a fairly flat surface to land upon. Here's what it looks like when it rotates. You can see the size of these big Saxum, these big boulders sticking out, because when they go around on the terminator, you can see them flash past. So they're very large stones. Again, we're looking at a rubble pile here. And again, we're looking at a diamond shape. And again, it's because the rotation is sufficiently rapid that material evolves from the poles to form an equatorial bulge. Here's some pictures of the Southern Hemisphere. It's a picture of the Southern Hemisphere. There are hundreds of them. If you like to look at pictures like this, go to the OSIRIS-REx website. You can download and buy the bucket full. I've just got 1 or 2 here. Here's a typically big stone, 7.5 meters in size. That's as big as a house. And they're everywhere. Look, the whole surface is covered with these things. And they're not all the same. You can see quite clearly the different sizes, the different shapes, and they're different colors. So this is another aggregated rubble pile. And one of the big discoveries from this mission, which was a complete mind blower, everyone was taken completely by surprise, is that Bennu is ejecting material. At about 3 o'clock local time on the asteroid, material is ejected into space. The principal investigator described this as the biggest surprise of my career. Some of these things are thrown up and they do suborbital trajectories and they land again. Some of them are ejected completely and potentially form a meteor stream. So one day we may see a meteor stream which we can associate with this particular asteroid. They range in size from millimeters to centimeters. So from grains of sand to stones, cobblestones, something like that. And this is not a fluke. I mean, if it just been seen once, you might think, oh, maybe there was a meteorite impact which just happened when the spacecraft was there. But more than 10 of these ejection events were seen in the first few months of the mission. So this is clearly a regular process. No one yet fully understands why they're happening. If it was a comet, you'd say, fine, it's gas evolving from inside, bursting out, blowing dust off the surface. But these are not icy objects. They shouldn't have trapped gases in large quantities. It may be thermal. The fact that they tend to happen in the late afternoon, that's when the solar energy has been piling onto the stones for almost all day. And it may be that they fracture because of the uneven heating. And sometimes they just go ping and throw some bits off. There's still a lot of work to do on this, but it was a big surprise to everyone. They also find from some of these many hundreds of photos that have been returned, some objects which are clearly interlopers, and they're just marked here. You can see quite clearly that there are some objects here on the surface which just don't look like they belong there. And they're probably in effect meteorites. They're bits of other asteroid that have been blasted off something else nearby in the main belt and landed on the surface here before Bennu was itself flung out of the asteroid belt and into an Earth-crossing orbit. But the main event is this sampling thing. This is a typical typical acronym soup. I'm not even going to waste my time explaining what all these things are. There are a bunch of cameras and spectrometers. The only thing that really matters is the trombone sticking out to the bottom left, which is the touch and go sample mechanism, TAGSAM. That's the thing that's going to grab the sample. And the big thing in the middle, that's the little Apollo capsule that's going to the sample return container that's going to bring it back to Earth. Here's the TAGSAM with a human being for scale. It's quite a big thing. You can see the main arm several meters long, and the sample mechanism is about that sort of diameter. Now they needed, in theory, they needed a flat area about 10 meters in diameter to make this sample attempt, because that was the uncertainty with which they thought they could control the thing down onto the surface. And the discovery that the whole thing was covered in boulders was a bit of a fright, because it was obviously difficult to find anywhere smooth enough to do this sample grab. On the upside, the engineers found that they could control the spacecraft with greater precision than originally thought. And so that relaxed the targeting requirements a bit. And they did eventually find several suitable flat areas. These were the top 4. These were the 4 shortlist. They're all named after birds. The final choice is the one in the top left-hand corner, so-called Nightingale. And the idea was to hit that trombone somewhere in that white circle, preferably in the middle. Remember that these spacecraft have, and again, if you've got a camera on, you can see me sticking my arms out. These have big solar panels which stick out on either side. So they've got to find an area which is flat enough that when they come down with that trombone, it doesn't hit the panels on a nearby rock. That's why they need a flat, smooth area to do the sample grab. Here's the sample grab itself. It takes place on the 21st of October. This is a still. I am going to show a movie. It's actually an animated GIF rather than a movie. But what you'll see is the spacecraft descending towards the surface, the TAGSAM being oriented at the last second to make it perpendicular to the surface, and then it hits the surface. And when it hits the surface, it blasts in some nitrogen gas. Remember, Hayabusa fired a bullet. The TAGSAM blows in nitrogen gas to stir up the dust and blow it into the horn. So here we go. Down it comes. Quick repoint any second now. And then whack. And you see stuff flying everywhere. Some of that's from the thrusters of the rocket, of course, from the thrusters of the spaceship, because the spaceship, after having done the sample grab, has to back away. And then there's the nitrogen gas, which is blown down to the surface to stir the stuff up and collect it. Now, you may know that shortly after the sample collection, there was a lot of concern that material was leaking out. This is an animated GIF. There's just 3 pictures which are repeating. The original plan, and this is a measure of how clever spacecraft engineers are. Now, I'm a scientist, I'm not an engineer, so I can say this with a completely straight face. These guys are really, really clever. The original plan was that after the sample grab, they would spin the spacecraft a little bit, and having and knowing what the spacecraft mass is before, and knowing what its moment of inertia is, and measuring the moment of inertia when they do it the second time, they can tell from the differences in the motion of inertia how much stuff has been picked up. I mean, how clever is that? You know, I want to weigh a teaspoonful of material, and what I'm going to do is I'm going to spin my car around, and then I'm going to spin it around again, and I'm going to look for the difference in the two spins, and that's going to tell me how much stuff I've picked up in the process. It's just astonishing. But what they found was, when they looked at the sample head, the material was leaking out again. And they thought, whoops, we've gone all this trouble to collect this stuff and it's leaking out. And if we start spinning the spacecraft, we run the risk of throwing out more stuff. So they didn't bother with that. They just said, we'll quit while we're ahead, and we'll store the sample straight away rather than risk doing anything clever. Now, my first reaction to this was, what on earth's gone wrong here? So I had to do a bit of digging around, and this is what I found had happened. This is an animation. It will repeat. So you see the tagsam goes down, then the nitrogen gas blows. Poof, there it goes. And the nitrogen gas picks up the dust, and it blows open two little red trapdoors to let the material flow into the sample containers. And what's supposed to happen about now is that these trapdoors close again. What seems to have happened in practice is that some large-ish stones got blown up as well and jammed those little trapdoors open. And that's how the material was leaking out. And that's why they decided not to do this spinning experiment. What they decided to do instead was to immediately store the sample head in the return capsule. And again, returning to my "isn't this just too clever for words" theme, these are real pictures from the spacecraft. They're not simulations, they're not lab tests. These are real pictures showing that the sample head, left-hand side, you can see it being lowered into the return container. Right-hand side, you can see it in position. Then the head is detached from the arm, and the lid of the sample container is closed. And the little Apollo capsule, little ice bucket sized sample return container, it's got the sample in it, ready to send it, but ready to bring it back to Earth. OSIRIS-REx drifted away from the asteroid for several weeks, but they did just eventually decide it was worth making one last flyby to see what they could see on the sample site. So here's a return to the return to the asteroid just for one rotation, just to image it as it rotated once again. And this is the sample site. X is where the sample head struck, and the thing that's in the red ring is a boulder or a rock or stone, whatever you want to call it, that's been clearly moved 10 meters, 30 feet by the impact of the lander and the stirring up. So it's clearly been a very dynamic process. So where are we with this? OSIRIS-REx departed Bennu in May. It's due back on Earth in September of 2023. The sample return canister is released a few hours before the spacecraft is due to crash into the Earth. Once the canister is released, it's on a collision course with the Earth. So the spacecraft then maneuvers, fires its thrusters to deflect itself away so that it doesn't crash into the Earth itself, but instead goes into a solar orbit. And I will bet you that they will do their best to then send it on somewhere else. The sample return container re-enters the atmosphere, or enters the atmosphere like an Apollo capsule. Heat shield slows it down, parachutes pop out. And in theory, with a bit of luck, on September the 24th, 2023, the sample capsule will land in the Utah desert, and the samples will be taken to the labs for analysis. The baseline is 60 grams, 60 to 200 grams. So they're hoping to have quite a lot more dust dust and rock than they got from Hayabusa, which, if you remember, only produced 5 grams of material. So if all goes well, it'll be a much larger sample coming back from OSIRIS-REx. I don't think a follow-on mission's been defined for OSIRIS-REx yet, but I think you can be pretty confident that, assuming the spacecraft's still healthy after the sample return mission bit's finished, they will try to send it somewhere else. That's always been the way. And just to wrap up, 2 or 3 slides on this latest mission called DART, the double asteroid redirection test. This is a part of the Earth Defense mission. It is specifically designed to find out what would happen if you deliberately impacted an asteroid in an attempt to deflect it. So you've all seen Bruce Willis going off to an asteroid with his atom bombs. In practice, that's probably not a very good way of doing it, but we don't know for sure how easy it will be to deflect an asteroid. And the fact that we now know that many of these things are rubble piles means that just bashing them in one place is not necessarily the right way to do it anyway, because you may just cause them to fall apart rather than move them somewhere. So this is simply an experiment to test it. And you'll see why it's called double asteroid redirection test in a minute. The target is this thing called Didymos. It's another Earth crossing or near Earth asteroid. It doesn't actually cross the Earth's orbit, so it's not a potential collider right now. And there's no real danger that the DART mission will accidentally knock it into a collision orbit either. So it's an ideal target for a test like this. And it's a binary. That's the trick. It's not just one asteroid. It's actually two asteroids orbiting this mutual center of mass. This is the spacecraft. It's only got one experiment. That's a camera. It's the same camera, or virtually the same camera as was used on the New Horizons mission to Pluto. And the purpose of this camera is to take as many pictures as possible of the asteroid in the few hours before the collision, because this is designed to smash into the smaller of the two objects, the moon of Didymos. And this is a very small moving target. And again, it's quite a long way from the Earth, so you can't joystick onto it. So the camera will, first of all, try to locate the asteroid, locate the satellite of the asteroid, figure out where the satellite of the asteroid is going to be in a few minutes' time, and then steer the ship into a collision. It's all autonomous. It has to be done very quickly because there's only a couple of hours in which the asteroid is actually close enough to be resolved. It's just a point until very close to the impact, at which point you have to separate the two halves, figure out which one you're shooting at, adjust your trajectory, and smash into it. There's a small sub-satellite provided by the Italian Space Agency, which will be released and will hopefully return pictures of the impact before it too flies past the system. And the idea here is simply, we know how much the spacecraft weighs, we know how fast it's traveling. What is the effect on the asteroid? By how much does it change the asteroid's movement? And that's why the fact that it's a binary makes so much difference. If you hit a single asteroid, you might change its velocity by a few centimeters per second, but it would be really hard to measure that. You'd have to measure the orbital arc over a period of months to get at, to see how much of a deflection you'd change. But because this is a binary, we can time, and it's an eclipsing binary, one thing passes directly in front of the other. We can time those eclipses from the ground with great accuracy. And after the impact, the orbital period will change slightly, so the interval between the eclipses will change, and that will very quickly enable us, or the scientists involved, to calculate by how much the velocity of the orbiting asteroid has changed. So here are a couple of diagrams. It's got an ion engine. So you launch it on a conventional rocket, it uses the ion engine to push itself out into a collision orbit. It heads off towards Didymos, and then it impacts. Here's the artist's impression of it smashing into the satellite of the parent asteroid. And in the little blue circle in the bottom is a ground-based telescope measuring the orbital period of the system to see by how much it's been changed. And it's quite easy, actually. Here are some models which show if you hit it hard enough to change the rotation period by 73 seconds, even in a few days, you can clearly see that the eclipse timings are not what they used to be. And if you manage to change the orbital period of the moon by 7 minutes, it's a piece of cake to see within a week how much of a change you've made to the orbit of the satellite, of the asteroid satellite. So that's DART. It's a quick mission. It's already on its way. I think the impact's in September. So it's not a long wait, not like some missions. We should know the results of this thing within a year. And just in passing, one of the co-investigators, principal investigator, there are two. One of them is called Andy Rivkin. I know Andy. He was a research student when I was a support scientist in Hawaii, and he and I observed together at UCURT. And it's funny because I still see him as a 24-year-old bright young thing, and of course that was 30 years ago. So he's now a 55-year-old senior astronomer. But it's funny, how it's such a astronomy is such a small world. You keep running into people. And that's it. That's all I wanted to say. I think I've been roughly on my 45-minute target time, and I'll stop the share in a second, and I'll do my best to answer your questions. I do have a bucket load of other more technical slides, which maybe I'll pull up if somebody asks me something very technical. But I hope it's not too technical, because if it's too technical, I won't know the answer.
Thank you very, very much, John. No, certainly I wouldn't say it's too technical. I really, really enjoyed every minute of it, and God, how quickly time has gone. So whilst we do have a few questions, any of you want to put some more in on the chat, then please do so. Just before we get to that, I can say that regarding the chances of being hit by an asteroid, I would just tell you that if anybody tries to sell you insurance, no, you don't need it. Something actually that I will ask, I don't know if you have the value. If not, I have looked it up, and that is, you mentioned how small Ryugu is. Do you know what its surface gravity is?
Oh no, I don't. Not off the top. I mean, I probably do.
That's okay. I just wondered whether it might be on Wikipedia, and yes, it is. And the answer is
5%, not very much.
1/80,000th of the gravity of Earth. So, that's why a vibrator of the type that you might have in a mobile phone will be enough to push something off the surface. It's quite staggering. I mean, really, both of all three of these missions are quite staggering, and certainly the camera work that we've seen from them, as you say, compared to what we used to see back in the 60s, it's absolutely staggering. It really is, isn't it?
Yeah, and the handful of pictures I showed are literally one of thousands. I mean, there are thousands of pictures of these things. Every blinking stone has been, oh, sorry, Jerry, every blinking rock has been photographed in excruciating the amount of detail. There are literally dozens and dozens and dozens of pictures I could show. I mean, truthfully, they all look pretty much the same, but there are, it's just fantastic. I mean, it really is. I mean, I grew up studying these things when an entire asteroid was one pixel, because it was a point source, now we can sit there counting individual grains on the surface. It's just terrific.
Okay, first question then from Anne Godwin. She's asking about the recovery for the sample return. Came down in the Australian desert. Well, suppose it had missed and actually come down in the ocean. She said, how would it have been recovered? I'm asking, could it have been recovered if it came down?
It's a good question, and I don't know. Would it float?
That's the thing, basically. I mean, it was completely sealed.
Yeah, I mean, that was fine. I don't know idea if it
had enough buoyancy so that it might have been picked up off the surface.
I don't know. That's a good question. I don't know. What I do know is that some of the other sample return missions, I think it was Stardust, the parachutes didn't open.
Yes.
On re-entry, and the thing smashed into the ground at terminal velocity, in effect. It had a switch and a backup switch. The trouble was they were both installed upside down, and neither of them worked. So the parachutes didn't open. So they did recover it, but they recovered it in a somewhat mangled state. I should look that up in case somebody, I'm giving this talk again in a few weeks. I shall look that up, in case somebody asks me.
Okay. Richard Shepherd has asked about the possibility of actually seeing Ryugu. He said, if the surface is dark as coal, do you know what magnitude it would be at closest approach as seen from Earth?
Again,
it amazes me how they get probes to such small and distant objects that you just cannot see.
Well, I mean, it is dark, but most of the asteroids are a few percent reflect. I mean, asteroid reflectivity is typically assumed to be about 10%, which mostly means somewhere between 4 and 15. The V types are much more reflective. They're actually 50% nearly reflective. I don't know the limiting. I don't know how bright it is, but I mean, it must be reasonably bright. Otherwise, we'd never have discovered it, right? I mean, this would have been discovered in a sky survey. One of these things that just covers the sky, looks for everything brighter than 20th magnitude or something, and then it's been observed often enough to define its orbit. So its orbit was already defined before, it was reasonably well defined before it was selected as a target for the mission. So I don't know. I mean, my guess is it'll probably be 17th or 18th or something like that. So out of range of most amateur telescopes, but
well, again, I looked this up on Wikipedia. It only gives absolute magnitude, which it says is, and it gives a number of values between 18.3 and 19. So not something you're going to see with
asteroid absolute magnitude is a funny beast. You as astronomers probably know that when we talk about the absolute magnitude of a star, we mean how bright it would be if it was 10 parsecs from the Earth.
Yes.
At a standard distance. So we do the same thing for asteroids. We say, how bright would this be if it was 1 AU from the Earth, 1 AU from the Sun, and at a phase angle of 90 degrees. Now you can't 180 degrees. In other words, it was a full moon. Now you can't do that because to get it, and you can't be a full moon if it's an AU from the Earth and an AU from the Sun. It's got to be over there somewhere. It can't be behind you. So it's a somewhat artificial construct. So that 18th magnitude is how bright it would be under this rather contrived circumstance. But I guess since it is 1 AU from the Sun most of the time, and it's probably not much more than 1 AU from the Earth most of the time, it's probably about 18. I mean, you could go into something like Horizon, the JPL Horizons database, and calculate its magnitude pretty easily for any given day.
Okay. And how one from Neil Harknett, who asked, could it be possible that the surface of the two asteroids you mentioned contain the largest rubble, and the closer to the center, the finer the rubble gets? He says, if you shake a cereal packet, the finer pieces of the cereal make its way to the bottom, while the bigger pieces make its way to the top. Is it possible that the spin of the asteroid will act similarly to shaking and force the larger boulders to the outside, while the inside is fine sand?
Funnily enough, I was going to counter exactly the opposite of that argument, which is that you're absolutely right with cereal packets. I know this because every time I tip the remains of my fruit and fiber into the next box, it's always very, very tiny grains. But of course, the cereal packet's not being spun very rapidly. So I suspect that the big rocks still finish up at the center, but it's definitely the spin rotation stuff that causes the boulders to fall down from the poles to form this equatorial bulge. That's why they're diamond shaped rather than sphere.
Yeah, okay.
Good question though, but I think probably not.
Yes, yeah. Kevin Noble says, I imagine if they can land it on a small asteroid, they can manage to land it in a desert in Central Australia. Well, obviously the landing in Utah is a much, much finer precision than a desert in Australia.
Yeah, no, I'm not concerned. I don't think there's much of a concern about this. I mean, we've been landing things back on Earth for 50 years. You know, some of them had people in, and I think that the navigation to just say, okay, we need to burn for whatever it is, 3 minutes and 17 seconds. I don't think that's a big problem. I mean, unless the motors fail for some reason. But I don't think there's a big worry there. I mean, the Stardust thing, they were originally going to grab the re-entry capsule with a helicopter.
Yeah,
while it was towed behind the parachute. So they had to be confident that they could get it within range of the helicopter. So I'm pretty sure they can put it more or less wherever they want. And again, fortunately, we've never had to do it in practice, but we developed technology to put large explosive devices on rockets and land them with fairly high precision in other parts of the planet in the 1950s. So I'm not worried about that bit of it.
They have a note from Neil Harknett. He says, this is an example of press scaremongering. A headline talked about an asteroid that was threatening to impact the Earth, but only as you read the article did they mention the asteroid was 400 million kilometers away at its closest point, which is further than Mars. Yeah, we do need to make sure that the press do the right thing when they're writing stuff, but
yeah, this is always
trying to do, isn't it?
This has always been a problem. When I worked on IRAS back in 1983, I had a conversation with somebody in 1983. I was looking with Simon Green, who was now at the Open University. We were looking for moving objects in the IRAS database, and the very first thing we found, I found it actually, was comet IRAS-Araki-Alcock, which was the closest approach of a comet to the Earth for 200 years. And I had some journalist, somebody rang me up and asked me a bunch of questions about whether it could hit, and if it did hit, what could we do about it? To which my answer was, no, it's not going to, and we couldn't do anything anyway. And he said, oh, well, that's another good story ruined by the facts, which I thought was rather interesting, rather interesting take.
Unfortunately, some people either don't understand facts or they don't listen to them or whatever. So on Quora, which is an online question and answer session, there's still people who write in saying, is Apophis going to hit the Earth in 2029 or whatever? And no matter how many times people write back and say, no, it isn't. Will you stop asking this? You still get people asking, is it going to hit Earth? No, for goodness sake.
Apophis asteroid 99942 was a potential Earth impactor, a potentially hazardous asteroid. There are a couple of scales, which there's a thing called the Torino scale, which was an attempt by asteroid astronomers to define something like the Richter scale. How likely is it and how bad will it be? Where 1 is, who cares? And 9 is, oh my God, we're all going to die. And virtually none of these things have got more than a 2. And even they don't stay on that scale very long, because after a bit of orbital refinement, we realize they're not going to hit us at all. So they very rapidly, even the ones that come up on the scale originally as 2 or maybe even 3, rapidly fall back down to 1 or 0 once we know the orbit. However, let's not be too cocky about this. I mean, we do know asteroids strike the Earth. We know the asteroids killed the dinosaurs. We know what happened over Russia a few years ago at Chelyabinsk, whatever it's called. You know, this thing came in, exploded in the atmosphere. Dozens of people were injured, mostly not by flying asteroid, but by flying glass, because they were all looking out the window when the thing went bang and the sonic boom blew the windows in on them. But, you know, asteroid strikes do happen. And one of these days, there will be a big one. Statistically, it's not likely for a couple of 100,000 years, but you know, statistics are just that. It could be tomorrow. It probably won't be, but it could be. So that's one of the arguments for DART. I mean, I gave this talk to one, or I mentioned the DART to my local astronomy club, and one of the guys sort of went, what a waste of money. And you know, my response to him was this: the dinosaurs didn't have a space program, did they? And look what
That's
happened.
it. And that's what who wrote Ringworld? Larry Niven.
Yeah.
That was his quote. The dinosaurs became extinct because they didn't have a space program. If we become extinct because we don't have a space program, it'll be our own fault. And that's it. Now, on the subject of science fiction and asteroid impact, some of you, I'm sure, will know of Arthur C. Clarke's book, Rendezvous with Rama. And in the opening of that, at some point, is it 2073? I can't remember the date. I do know it was the 9th of September. So this was the original 9/11.
It's just outside. I can go and get it if you want.
Okay. So an incoming asteroid destroyed Venice. And it was decided this will not happen again. And so Space Watch was set up in order to look for potentially hazardous asteroids. And it was because of that book that the real Space Guard was set up. And the UK part of that is just over the border in Wales.
Jay Tate, isn't it?
Sorry?
Jay Tate.
Yeah. Jay Tate, who does fantastic work there. Now, Morgan Freeman wanted to make a film of Rendezvous with Rama about 20 years ago, and it's been in development hell almost ever since. But just recently, a new company has taken it on, and the guy, oh gosh, I've forgotten. He did some major film recently, and he's got a follow-up to that. And after that, he's going to do Rendezvous with Rama. So I look forward to seeing that. 2023, I think he's starting on it.
I would look forward to seeing it if it's a film dominated by story and not by special effects. That's the problem with fiction films these days, is they're 90% special effects and 10%. I mean, people make fun of early Doctor Who's, but actually the Doctor Who stories were actually quite good. It was the special effects that were rubbish.
Yes, although it has to be said, though, that with Rendezvous with Rama, special effects are going to be a really major part of it. It was allegedly, I saw this back in the 70s, written by Arthur in response to a challenge by Stanley Kubrick to write something that he couldn't film. And Stanley read it and said, no, you just need to project the cylinder and it's easy. But anyway, okay, we haven't had any more questions come in, so I think we'll pull things to a close. On behalf of everybody here, I want to say a terrific thank you, John. It has been really, really enlightening and interesting. Thank you very much indeed.
Yeah, well, my pleasure. And to those of you who are taxpayers, thank you for paying my salary.
Can I say thank you very much indeed again, John, and thank you, Jerry, for introducing and arranging such a terrific meeting. I'm sure we've all enjoyed it ever so much and learned a terrific amount from this evening's programme. As we said earlier, it is being recorded and will be put onto YouTube by the weekend, hopefully. That brings our meeting to an end, other than to remind you that our next meeting is on February the 9th, when we've got Robin Catchpole coming along, and he'll be talking from here to the edge of the observable universe. Well, to do all that in 45 to 60 minutes, I think is going to be some event, isn't it? So make a note of that in your diaries, February the 9th. So on behalf of the Hartford Astronomy Group, can I thank everybody who's made this evening possible, particularly the committee who work tirelessly in the background to get things going, and especially to our guest speaker, John, for making our evening such a pleasant one. So thank you, everybody, and good night.